guest lecture series presented by Kshitij, IIT Kharagpur. I, Devan Singh Faujdar, would like to invite our guest, Dr. Dave Patterson, to today's session. Dr. David Patterson is a UC Berkeley professor, a Google Distinguished Engineer, and the RISC-V Vice Chair. Dr. David Patterson, with his most influential Berkeley projects likely were RISC and RAID. And his best known book is Computer Architecture, a Quantitative Approach. And with this introduction, I would request sir to take up the session.
All right. Good evening, everybody. I'm calling you early in the morning in California. It's still dark a little bit. So the talk I'm going to give about is going to talk about it has two pieces to it. It's going to talk about the lessons learned about machine learning, both the hardware and the software, and then talking about the carbon footprint of machine learning, which is a topic that a lot of people have been interested in. And you can see in my title slide, if you're interested in going into details, it's based on papers that are available publicly if you'd like to take a look at them. All right. Oops. Okay. So the first, it'll be about ideas. It'll be about 20 minutes where I talk about the TPUs, and about 20 minutes where I talk about the machine learning carbon footprint of it, and then I'll open up for questions and answers. So it's so be ready for questions here. So how did the TPUs get started? 10 years ago, Jeff Dean was an early believer in these deep neural networks, and he calculated if 100 million of users started using their phones 3 minutes a day to use machine learning, that Google would have to double their data centers, which would be very expensive and take a long time to do. So the idea was to create what we call today a domain-specific architecture. That is, a special purpose computer just for deep neural networks that would reduce the cost of ownership by a factor of 10. Now, deep neural networks have two phases. There's training, where you make them smart, and once they're smart, you call it inference or serving. And this was just on the latter one. This was on the inference or serving phase, making it factors of 10 better. So they started kind of an emergency project, and kind of remarkably, in 15 to 20 months, they did everything. They come up with the architecture, do the compiler, do the software, build the hardware, and deploy it in the data center. It's still remarkable that they did it that quickly. And they actually exceeded their goals. We subsequently wrote a paper about it, and it was about a factor of 80 the performance per watt of CPUs, and about a factor of 30 over the contemporary GPUs. So they overshot their goals. Now, what happened is that in May 2016, our new CEO, Sundar Pichai, decided we would tell the world what we were doing. So just a year later, and I hope this video will work, but through the magic of YouTube, we can go back to that date in 7 years ago to hear how he introduced it.
And by the way, when you use Google Cloud Platform, you not only get access to the great software we use internally, you get access to specialized hardware we build internally. And talking about that, for machine learning, the scale at which we need to do computing is incredible. And so we have started building specialized custom hardware. We call these tensor processing units, or TPUs. TPUs deliver an order of magnitude higher performance per watt than all commercially available GPUs and FPGAs. And when you use the Google Cloud Platform, you can take advantage of TPUs as well.
So that announcement was shocking here into the world and to Silicon Valley. So those of you who know Helen of Troy, this is a picture of Helen of Troy, and the poet says, the fight over her led to the Trojan Wars. And so hers was the face that launched 1,000 ships. And I kind of, as a pun, say that the TPU launched 1,000 chips. Intel, caught flat-footed like everybody else, started buying domain-specific architecture companies. Nirvana, Movidius, Mobileye, and now more recently Habana. So billions of dollars to try and catch up. Two of Google's competitors that are hyperscalers, Alibaba and Amazon, decided to build their own inference chips. And then the venture community got involved, and more than 100 startups. They invested about $3 billion per year, and they all had their kind of interestingly different computer architectures that were funded to investigate things that maybe didn't work for general purpose computing that might work for these domain specific architectures. And then the paper itself was inspired a lot of work in academia, and it has, even though it's just, I guess, about 6 years old, it's got more than 5,000 citations, which is remarkable. So it was a very influential first step. Google has since announced 5 different products around the TPU. You can see the 2 of them there are for inference, the TPU v4 and the TPU v1. And then the other 3 are for the harder problem of training. And there's 3 generations of them. And each time they went from, they increased the number of chips by a factor of 4. So the TPU v2 was 256 chips, TPU v3 was 1,024, and TPU v4 was 4,096. I think just in this last week, Google announced that the next generation of inference in chips. It's not on this slide. So what have we learned from all that decade of building TPUs? Well, we split it up into 10 lessons. 5 of them are about the models themselves, the first 5, and the next 5 are kind of about hardware and architecture. So given the time format, I'm not going to go over all of them, but I'll go over many of them. So the first is these deep neural network models grow rapidly. It's much faster than standard software. So for the models that were existing, we looked at 4 years apart, and they grew about 50% per year in memory capacity and compute. But that was for kind of the inference serving phase. For the training phase, at the state of the art, it's growing even faster than that. You've heard, everybody's now heard about GPT-3. So what was the big idea of GPT-3 over GPT-2? It was just that it was bigger. It was the parameters, one of the key metrics, it was 100 times as many parameters. And so there's been this thrust towards much larger training runs. So basically, but the lesson is, you better design computers to allow for the models to grow, because computers will last, 3 to 6 years, and the model's going to keep getting bigger over time. And then it's unlike standard software where, the software changes very slowly. Compilers aren't that different now than they were 5 years ago or 10 years ago. The mix changes dramatically with announcements because it's a younger field. So one example is BERT, which is one of these exciting transformer models that was published in 2018. 2 years later, it was 1/4 of the Google internal workload. So it's just, things change remarkably fast. And you can see that the LSTMs that were almost 1/3 of the workload in 2016 have disappeared because they got replaced by the transformer models. So it's very rapid changing, unlike traditional software. So that means if you're going to do hardware software systems, you got to be flexible because something new may come along you have to accommodate. And one of the interesting differences from the traditional background, where you can change the compiler and the hardware, but the applications are sacrosanct. You can't change them. That's not true for deep neural networks. As long as you maintain the same quality or improve the quality, they're okay with you changing it. I think part of the reason changing is feasible compared to traditional software, it's hundreds or thousands of lines of TensorFlow or PyTorch is how you specify it. It's the smarts is the training. It's billions of parameters is where the smarts are. It's not millions of lines of code, so that's easier to make the change. So one example of this kind of adaptability is a paper here that's called Platform-Aware AutoML. It's where you use ML to search a very large design space. What you're trying to do is adapt the neural architecture, the deep neural networking model, to the hardware. So you make the hardware make the model match the hardware, which you can only get that with compiler and traditional ones. And so they made that model run 60% faster, 1.6x faster, just by the hardware was the same, the compiler was the same. They just adapted the model to make it fit better on the hardware. So that's a nice characteristic. One of the things for this inference phase is you're often dealing with individuals, so the latency is important. So there's a service level agreement about what, like 99% of the queries have to be done that time. So there's been some papers published in the hardware area about batch size. So what's batch size? Batch size is you put a set of tasks together that can amortize the fetching of those, use those same weights that you fetch. So you want to amortize them together to run more efficiently. And so some have argued to get the best latency, you should keep batch size to be only 1, where you don't get to reuse that memory access. Well, that would be the best latency, but the requirement isn't the best latency, it's the time limit one. So as you can see for these examples, for both our production deep neural networks and even the ML-perf networks, batch sizes can be 16 to even 500 and still meet the latency limit. So basically, not surprisingly, the latency limit is based on time. The batch size can be much better, which means the hardware can run more efficiently. And then the final lesson is some people will think about just running a single model at a time, but that's not the real world. Just like CPUs run multiple jobs, accelerators have to be able to run multiple models. And so you need to very quickly switch between models. So like for translation between different languages, it's not just going to be English and French or English and Spanish. There'll be lots of combinations. So you want to have lots of models there. And there's other reasons for that. But not surprising, like CPUs, you got to be able to run multiple models at once, not just one at a time. And so we looked at, in the paper, we found these 8 applications that kind of were typical of the production models being run, and you can see that 6 of them were multi-tenant that they had to switch. And you get one from an architecture perspective, like, well, maybe we could just fit these models all in the chip. Collectively, if they all fit in the on-chip memory, then it wouldn't be that big a deal switching, but they don't. What you can see in this slide, I draw a line typical how much memory might be on a chip, and the kind of the working set, the footprint is much larger than you can fit in SRAM. So you probably need to have a fast DRAM to swap between models because multi-tenancy is a practical requirement. Okay, all right, we got through the first 5 lessons. Let's talk about more of the hardware stuff. So this title is a paraphrase of the Bill Clinton presidential campaign, where he said it's the economy stupid. And I'm saying it's the memory stupid. So kind of what happens in terms of when we brag about hardware, we often just brag about how many floating point operations per second, how many flops we can have. But in the way, but for hardware today, it's not really limited by the number of transistors. It's more limited by the power what you can deal with. And so what we want to know is how much energy do you use per operation? So it turns out that going off chip to external DRAM memory takes tremendously more energy than anything you do off chip. So even compared to on chip memory, it's a factor of 100 when you have to go off chip, go over the pins and come back. And if you compare it to an arithmetic operation, it can be a factor of 10,000 versus an add or a multiply. So if energy is the limit and we have to go off chip to get the DRAM, well, what do we do? What we do is we put lots of arithmetic units there because they use so much little energy. So we have tens of thousands or even 100,000 arithmetic units. So it's very easy in modern technology to scale up the flops. But what the real challenge is the memory bandwidth. How do we get lots of memory bandwidth and fit it within the energy budget? And so then if we have tens of thousands or hundreds of thousands of arithmetic units, how should we organize them? Well, the CPU designers knew their computer history and went back to an idea from the 1970s called systolic arrays. You can think of what's shown on the left as a single dimensional pipeline, the conventional pipeline you read about in textbooks like mine. Well, the systolic array is to have an idea of a 2-dimensional pipeline. And if you carefully choreograph when the data and partial products arrive, you can very efficiently do matrix multiply. And matrix multiply is at the heart of the deep neural networks. That's the fundamental operation that's going on. So it was originally invented to be more area efficient, but that's much easier to do today because we have lots of metal layers. But it's very energy efficient. It's about twice as good and energy efficient if you use systolic arrays. And so systolic arrays work really well for us. What we keep do is increasing the number of systolic arrays, either more of them over time, because it maps well into modern technology. Okay, and then the compilers plays an important role. There's no off-the-shelf compilers for machine learning. There are for like standard CPUs. There's LLVM and GCC for standard processors, but that doesn't exist for this deep neural networking models. Google invented its own, NVIDIA invented its own. Theirs is called CUDA, ours is called XLA, and it divides the optimization into high-level operations and low-level operations, and the high-level operations work on anything, and the low-level operations will be different for CPUs, GPUs, and TPUs. And it's remarkable the parallelism that they try, and the compiler tries to keep these balls all juggling in the air to get the maximum performance. There's multi-core parallelism. There's 4,000 chips on TPU v4. There's data level parallelism. There are these 2D vectors, right? And so you have to kind of lay out your data appropriately so you can get good use of these 2D arithmetic units. There's instruction level parallelism, and it's something called very long instruction words. So it's 400 bits, so it can specify dozens of operations within a single instruction. And with this 2D, the compiler challenges is having good layout and memory to match these two registers, 2D vector registers, which is a new challenge. And there's no caches in this thing. CPUs, depend upon the caches. That what you've accessed, you're going to access again, and they have 3 or 4 levels of caches. And it's a big part of the resources and of the performance of CPUs. But there's no caches. This is more predictable. So the XLA compiler just manages all transfers as DMAs. So these are pretty new stacks. How fast are they changing? And so here shows 2 generations of the ML perf performance benchmark, which are about 15 months apart. And over these benchmarks, they both the CUDA compiler from NVIDIA and XLA kind of doubled performance. So the hardware was the same. Advances in the compiler were able to double the performance, which is very fast. For off-the-shelf compilers for CPUs, if they grew 10% in a year, that would be a big success. It's usually much less than that. Okay, so I've covered the lessons learned, and let me just say how the TPU used them. Remember, the models grow rapidly, both for inference and training. And what Google did is put 4 times as many chips per these supercomputers pods, kind of double the performance per chip, and doubled the memory capacity. It's called high bandwidth memory. The models can change quickly anytime there's a research breakthrough in this relatively young field. And so you try to make it easier to adapt models by getting rid of bottlenecks with each generation, making the job easier for the compiler. You can change the model to adapt to the hardware. And so we take advantage of that and have machine learning techniques to do that. Kind of sensibly, you can have larger batch sizes. The service level agreement limit is based on latency, on time, not on the batch size. And you need multi-tenancy. Remember that. We'll bring back the flops are easy. The memory is hard. Remember that. We'll talk about that soon. The technology is changing. Different pieces of technology are changing at different rates, but for these array multipliers are working pretty well. And the compilers play this important role and are improving rapidly. Okay, so with that, let's make this transition to talk about the carbon footprint from machine learning, particularly for training, which is the phase of it. Okay, so how did I get into this? Well, the flagship publication of the IEEE, one of the largest computer societies, is IEEE Spectrum. Everybody gets it who belongs with that. And in 2021, it had this remarkable prediction. It said that if we took the models from 2021 and we tried to cut the error rate in half, kind of double the quality, training that model 3 years later, like they predicted that next year the cost of training a model would be $100 billion and have as much carbon emissions of the city of New York in a month. So that was, I couldn't believe it. So I asked my ML colleagues, is this true? You know, this is a pretty shocking prediction. And they said they didn't think so, but they didn't really have any data. So you think that's shocking. This was topped just 3 months later by a white paper that extrapolated to 2026 from 2021. And they said, to train the largest model, it would be more than the gross domestic product of the United States, so $20 trillion. And so $20 trillion, and imagine what the carbon emissions be if you spent $20 trillion do it. So these are startling predictions, and so that got me involved and some other people. Let's try and get to the truth of this to see what's going on. So to put this in perspective, it reminds me of this cartoon from a kind of a technology-oriented cartoonist called Kshitij. So what he did was similarly try and look up these predictions in the future on these log scales and illustrate what could happen. So he looked at the word sustainable in English text, and he looked backwards in time to the present day, and then drew a straight line on this log scale about how frequently the word sustainable would appear. Well, he said, if I go on this straight line log scale, 15 years from now, the word sustainable would appear once per page of English text. Of all English texts, you'd find on average the word sustainable once. All right, well, that's surprising. He said 40 years from now, the word sustainable, that would be every sentence in English, the word sustainable would have to be in every sentence. Well, that sounds hard to believe. And then 90 years from now, all of English text would just be the word sustainable over and over again. That's all you just see, sustainable, repeatable. And so the conclusion of this cartoonist is the word sustainable is unsustainable. I think the lesson learned is just the danger of extrapolating trends in the future, assuming there's no innovation there. Okay, so with that context, let me go ahead. So what we're talking about is the use of hardware. We're not talking about the manufacturing of hardware. I'll mention that later. Now, this is generally under the area of responsible AI. It's a very broad topic. It covers fairness and all kinds of other issues. I'm just talking about the carbon emissions from training, operational emissions from training. And so I've mentioned the operational and embodied here. A reason that we concentrate on the operational training is that's what those startling predictions were about, whereas the operational costs from training. And how do you measure emissions? It gets measured as metric tons of carbon dioxide equivalent emissions, so CO2e. So what is the equivalent emissions? That's to compensate for the other greenhouse gases like methane and nitrous oxide. So they converted this common form, but the metric will be tons of carbon dioxide equivalent emissions, that TCO2e. Okay, so how do we figure this out? Well, it's pretty straightforward. It's we're going to calculate the energy first, kilowatt hours. That's hours to train. Okay, that's the right unit. It could take hours or days or even months to train. How many processors you're using? Okay, that's pretty easy to measure. The average power per processor. So you'd want to measure when it's running for weeks or months, how much power does it use on average? You multiply those together, and then there's one more factor, and that factor is how efficient is the data center that you've got the computer equipment in. So the industry standard metric is called power usage effectiveness, PUE. And so what that's trying to measure is this overhead. So if you think of, if for every kilowatt going into the data center that goes to the computing hardware, if 50% of it is use of that energy, or if there's a tax of 50% of that energy for use for cooling or for power distribution, you'd say the PUE is 1.5. And so kind of, when they first started this, the PUEs for data centers were 2.5. So it's like 150% overhead, and it's gotten much better over the years. Okay, but those three factors, if we show you some examples of what the average power is for TPUs and GPUs, but hours, processors, average power times the PUE of the data center, and that's the energy. How do you get the carbon emissions of it, these tons of carbon dioxide equivalent emissions? Well, you just multiply the energy by a factor, which is the carbon emission per kilowatt hour. And that is a function of how clean the energy is going into the data center. So where do you get this data? Well, the other ones you can kind of figure out on your own. Google publishes the PUE and Facebook publishes the PUE. The carbon emission per kilowatt hour, you have to ask the data center operator. Google publishes the percentage of carbon-free energy, how basically how much renewable energy is being used at a given data center, which is closely related to the carbon, tons of carbon per kilowatt hour. Okay, so that's how we calculate it. All right, so what we've learned, we've captured in a mnemonic called the 4 M's. And if you follow these 4 M's, you can dramatically reduce the energy use and carbon emissions. What we did is we took a look at an effort that was done by people at Google to try and reduce the carbon footprint that was being done. And you can make a big difference here. So the first M is the actual model itself. So Google discovered or invented the transformer model, a very influential model. The T in GPT-3 is for transformer. And 4 years later, they had something that had the same quality, just as good, but was 4 times as fast. So that's, you get this 4 times reduction in energy by having the best model. The second one is the machine, kind of what I do. If we look at back in 2017, if you had used the NVIDIA P100 GPU, and instead, 4 years later, you use the latest TPU, there's another factor of 14. So just those 2 factors together reduce the energy almost by a factor of 60, a better model and better hardware, a better machine. The next one is to talk about this PUE factor. We use the word mechanization, but it's actually the PUE. So the global average in 2017 compared to Google's data center is about a factor of 1.4. So Google is about 1.1, only a 10% overhead for its data centers, but the average data center is about 1.7, 70% overhead. And the last one was the biggest surprise, which is MAP, that the kind of how clean the energy is hugely variable depending where you are geographically. So if you're near a hydroelectric dam, it'll be very clean energy. If you're near a coal-fired plant, it'll be very dirty energy. So you could get another factor of 9 by compared to the average data center if you used Google's in the middle of the United States where it's very windy. So if it's windy, daytime and nighttime, there's a lot of renewable energy, so it's an effect of 9. So you multiply those 4 metrics together, and 4 years later, it wasn't thousands of times worse. It was almost 1,000 times better, 1,000 times less energy by optimizing these 4 M's. The paper that did this, we also looked at the beginning of these large language models. GPT-3 is one of them that's got a lot of publicity, but it had inspired lots of competition. One of them is called GLAM that Google did. So the GLAM people thought they had better accuracy in GPT-3 because they had many more, even more, like more than a factor of 7x more parameters. So they had more parameters, so seems like it would work better. So so 7x the parameters, but surprisingly, they were able to do it in they cut down the compute time by a factor of 3. How did they do that? Well, that's because the old models they're called dense models, and the new ones are sparse models. The particular model is called mixture of experts, where you have, say, 16 experts, but you're only using one of them at a time, say 1 or 2 of them at a time. So you only have to access 8% of the parameters per token. So that reduced the compute by a factor of 3, that reduced the energy consumption by a factor of 3. And then because GLAM was trained in this more efficient Oklahoma data center or one of the other data centers, there was another reduction. So overall, it's about a factor of 14 compared to the training of GPT-3. So again, here it is 18 months later, it didn't get a lot worse. If you follow the 4 M's, it can be 14 times better. And then how do we put these, when we talk about metric tons, how do you put these into perspective? So in the US, the Environmental Protection Agency has a calculator, and basically, one way to think of it is for a car, driving a car for a year, how much carbon emissions from driving a car for a year. So the 552 tons is like 123 cars. The 40 metric tons for GLAM is the equivalent of 9 cars. And to put this in perspective, there's 1.5 billion cars in the world, and this is, we're talking about tens of cars or hundreds of cars. So in the big picture, this is small. Now, when I started giving these talks, and I said, okay, this is interesting, Dave, but how much of Google's energy and carbon emissions goes into machine learning? So we were able, because people asked that question, we were able to figure it out. So we looked at the same week in April in 2019, 2020, and 2021. And how were we able to figure out how much was machine learning? Well, virtually all of the training and almost all of the inference is on TPUs and GPUs. We also do some inference on CPUs, but fortunately, Google has this thing called Google-wide profiling that measures every subroutine you use and how much time you use it over time. So that's stored there. So we were able to look back in time and figure that out. And so to our surprise, each year between 2019 and 2021, the pie chart looked like this. It was between 10 and 15% of the energy was for ML, the rest of it for other things that Google does, like YouTube and documents and things like that. And so the pie got bigger every year because you get more customers, but the slice for machine learning remained under 15%. A question that people had is how much of it was for inference and training? At Google, it was 3/5 of that 15% or less was for inference and 2/5 for training. Now, when we started sharing these results, there was a research meeting at Stanford and about machine learning, and the students there said, well, it looks like if it's only 15% of the energy, then machine learning is kind of trivial. I'll work on something else. And so the Stanford friends said, hey, what's going on? So I said, wait, that's not the conclusion. Remember, it's not the flops, right? It's the memory accesses that are the big energy use. So because we had dedicated hardware, we were able to reduce the floating point computation to be much more energy efficient. So it was probably 70 to 80% of the flops. So the computation was 70, 80%, but it was only 10 or 15% energy because of the domain specific architectures. And that goes back to one of our lessons. Okay, now, how does your results mesh with those dire predictions? And where did those dire predictions come from? So now, basically, because global climate change is really important, we need to make sure we get the numbers right so that we work on the biggest challenges. So I'm going to need to, even though I'm a senior person in the field, I'm going to have to point out some flaws in some of the work by some younger people because, global climate change is important. We got to work on the right thing. So there was a study that was done by a group at the University of Massachusetts to try and understand the carbon footprint. So the paper they looked at was actually done by Google, and they were looking for what's called neural architecture search. I think I talked about that earlier. You try and find a better model to adapt to the machine. So they were starting with the famous transformer model and trying to find a better one. The same group came up with primer that I talked about earlier in 2021, but in 2019 they came up with what they called evolved transformer, which was I think significantly better, like maybe a factor of 1.3 better than the original transformer. So the neural architecture search is searching for a new model. So that's done rarely, right? Oh, here's a new problem domain. So spend a lot of cycles, and what you hope to come up with is a more efficient model as a result of that investment. But then people use that model many, many, many times. Okay. So that paper didn't include anything about energy or emissions. People hadn't been sensitized about that about 2018. So concerns were likely raised about carbon emissions of ML since that was growing. And so a group at the University of Massachusetts decided to estimate what were the emissions for the search for evolved transformer. And it's a very popular paper, cited, it's just a couple years old and almost 2,500 times. You can see its growth over time here. Now, they didn't have access to Google, the 4Ms of Google, so they just estimated it based on the average. So they used the P100, the GPU, they used US averages versus the Google Data Center PUE or the energy cleanliness. So because they use US averages, it was a factor of 5 too high. They didn't have Google's 4M. So that's that's pretty understandable. That's not that big a deal. I mean, they could have contacted Google to get our numbers, but they didn't. That's okay. Unfortunately, they didn't understand how search was done. Originally, the way neural architecture search was done, it was kind of brute force, and you used the full-size model to search the space, but that was expensive and slow. So neural architecture search got more efficient over time. And so the Google people used a small proxy for that search that was much more efficient. And in fact, it was 19 times more efficient. So that actual paper was off by a factor of 88, 19 because they didn't understand the search. That was a mistake on the paper authors, and 5x because they didn't ask for the 4Ms for Google Data Center. So, okay, so that's off by almost a factor of 100. Well, that's not, the story doesn't end there. Unfortunately, this widely cited paper, they didn't understand what a neural architecture search was. They thought it was the training of the model that you discovered. So they thought it wasn't the search for evolved transformer. They thought that's how much energy it takes to train evolved transformer. And that's a bad confusion, because the emissions from training is 1,300 times less than the emissions for searching the model, right? Searching is much more expensive than it was actually the model you ended up with. So when you multiply those together, it's 120,000, right? 120,000x too high. So where did that, $100 billion training, it was based on this paper that was off by 120,000. Instead of, the estimate was almost 250,000 kilograms, almost 250 tons. And one of the things that was quoted when people misunderstood it, they said, well, that's the carbon emissions of 5 car lifetimes, manufacturing the car. That's how much that is. In reality, it wasn't. It was 2.4 kilograms, it's hardly anything. And one of the reasons I started giving these talks was that we don't really have a good way to correct the record, right? So this paper's been published, it's highly cited, but we don't have a way to put a little gold star on it and say, hey, there's some mistakes in this paper. So I've been trying to give talks, and you can see so far got 20, in last year we had 29 citations. So the word's not out, and the other one's still growing rapidly. So yeah, this is just saying the same thing again. It's that the reality isn't as bad as it seems. So what does that mean? Well, first of all, it means that I've done some work both on the data center and the smartphones I didn't present today because of this miscalculation, because we thought it was really bad. So if that's not the problem, does that mean there's no problem in information technology? We're off the hook. No, it's just, the attention was focused in the wrong spot. We think it's much more likely that the manufacturing of computing equipment is our big carbon footprint issue, and that's the thing we should be focusing on. So I looked at 2021, and amazingly, we produced 1.7 billion smartphones, 1.3 billion smartphones, and 400 million featured phones, and they have a lifetime of 2 or 3 years. So all that huge carbon investment, and we discard them. So maybe we're discarding 1 billion cell phones a year. PCs, almost a third of 1 billion. They have a little bit longer lifetime, and 12 million servers, which have a much longer lifetime. So I think probably, if we're worried about our carbon footprint, we should be paying much more attention to seeing what we could do about the embodied cost of carbon, rather than worrying about the operational cost of training. Okay, so just wrapping up the talk before I get to the question period. So started off with these 10 lessons, 5 about the deep neural networks, the models, 5 about the hardware, and this big result is the flops are pretty easy to handle and make energy efficient, but the memory is hard. Google, for 3 years, ML dominates the computation, but because of that, we are able to keep the energy costs low. And then, so advice going on, people working on all the 4 M's here. Models, these are really important. Keep building more efficient models by factors of 2. And with these giant models needing really attention, I would focus on the memory rather than the flops. And then, if you're going to do one of these papers, why don't you publish the energy consumption carbon footprint so that we get competition beyond quality, but reducing the energy footprint, and to make sure we get the right answers, because people, if they calculate it afterwards, can be off by gigantic factors. People who do what I do, build faster, more efficient hardware. GPUs and TPUs can, each generation can be much more efficient. And then data centers are already pretty efficient, with 10% overhead, or at least the cloud data centers are. But it'd be great to publish how clean the energy is, and hopefully we would use the greenest energy centers. That kind of the easiest thing in the cloud to change the location. And I think if, as customers give preference to places with green energy, that'll encourage companies to build more data centers in locations with green energy. And then finally, if we can, co-optimize these 4 M's, we can deliver on this amazing potential of ML, the exciting potential to get positive impact in a lot of fields in the sustainable manner. And with that, let me thank all the people who, TPU, including the following, who built this hardware that I'm talking about today. And with that, I will go to questions. Okay.
Thank you so much, sir, for the lecture. I truly believe that your words will inspire a lot of us. Now, one question which I had was, how do you envision the future of ML, balancing its tremendous potential with the environmental concern it raises?
Of ML, is that what you said? Yeah. Well, I think if we're talking about the operational of ML, I think that's working out pretty well. So I think I might have, let me just see if I've got this slide here, because I've been talking about the kind of the cost of ML. So what are the positives of ML from an environmental perspective? So let me give you this one example. This was just published by Google. So contrails are those streams behind jets in the sky. So kind of remarkably, those contrails contribute to global warming. That they act like clouds and reflect sun and capture heat. And amazingly, 35% of the carbon footprint of aviation is the contrails. I never would have thought that. Now, when do contrails happen? It only happens when planes fly through these humid regions. So Google used AI to predict paths for planes that avoided some of the humid regions. And they did this study with the help of American Airlines in the United States, with 70 test flights over several months. And what they found is they could just edge, if you take a longer flight, you're going to spend some more fuel. So, but they could adjust this just a little bit. So they thought it was, 1/3% more fuel for the whole fleet to reduce the contrails by a factor of 50. So one of the figures of merit for carbon emissions is how expensive is to save a metric ton of carbon dioxide equivalent emissions. So this cost them, tens of dollars, whereas today, if you were trying to extract CO2 from the air, it's on the order of $1,000. So it was very cost effective to do that. If we hypothesize that aviation has a huge carbon footprint, if we hypothesize that all planes would use this AI, we could save, this single AI invention could save 170 million tons. So data centers, all data centers use about twice that. So this one idea could save half of the cost of data centers. And as you saw before, ML, at least Google data centers, if Google is typical, it was about 10 or 15%. So if this is all true, as far as I know it's true, this invention can more than compensate for the cost of ML and data centers, which is pretty remarkable. So there's upsides to smarter, smarter systems. It could help with the environmental problems, but people have been concentrating on what the costs are of those systems. But there's counterbalancing forces here. Did that answer your question?
Yes, sir. That was that really cleared my concept. And we will be moving forward with some questions from our audience. So our chat is just open. And if anyone wants to ask sir anything, he can text in the chat box. I'll just convey it to sir.
Just need that first question from the audience to get things rolling.
So until our questions come, I just wanted to ask, how do you see careers opening up in the future in this field?
Careers? Yeah, I'd say there's kind of there's this huge excitement about these large language models and what they're capable of doing, and can we make them safe to use and all that. So I think understanding the large language models and how could you, where are they useful, where are they not useful, that's kind of almost anybody can do that. You don't need a deep technical degree. How do you do the prompt engineering? How do you ensure that works is going to be kind of an immediate use case. I would say, participating, those of you in computing, is there's either, like I said, with the 4 M's I'm talking about, is hardware stuff like what I do, getting in and trying to do the models or invent new models or figure out how to use the latest models for your applications. Can we make data centers more efficient? Can we figure out how to use clean energy? An example of the clean energy use is typically renewable energy will vary by time of day, how much is available. Like if it's solar, obviously it's not available at night, and depending on wind. And so Google's had efforts to shift computing to different times of day or different geographic locations, depending on the availability of clean energy. And those are examples of kind of imaginative in this new world where, global climate change is this big deal. We need to do things differently than in the past. What kind of flexibilities do we have, and how could we reduce our carbon footprint and still deliver, exciting computing technology for important problems?
Sure, so I definitely think this will also help a lot of the audience. And now moving on to the next question. So, sir, what are the main sources of energy used for training ML models? Falgun is asking this.
Did you say what are the sources of energy?
Sir, I said, what are the main sources of energy used for training ML models?
Yeah, what are the main sources of energy? So one of the things when I read that article in IEEE Spectrum and they're making these claims, it was like, well, boy, that sounds pretty bad. I'll try and figure out what's going on in Google, and I didn't know what to expect. I was kind of, maybe we're going to uncover some really bad practices. So fortunately, for Google, what I found out, and I think for a lot of cloud companies, is they care a lot about the carbon footprint. So first of all, like I said, 15 years ago, the PUE, the power usage effectiveness, on the average in the world was 2.5, and I think at Google, when Google got into it, it was maybe 1.7 or something like that. So they brought down the energy overhead in their data centers pretty dramatically, almost to, perfect would be 1.0 and they're at 1.1. So that saves Google money, but it also reduces the energy footprint. The other thing that I found out is Google has this program that they call 24/7 carbon-free energy. So there's in the environmental things, you can do carbon offsetting, but the kind of conventional one is to say, well, as long as it's like in a very hot part of the United States, I'll use energy in the middle of the summer in a place that's very warm, like maybe Bombay or something like that. But I'll offset it by going up into the Himalayas in the winter and say I'm going to make an investment there, and the carbon savings in the winter in the Himalayas versus in the summer Bombay, they trade off 1-to-1. So that's, people aren't all that impressed. So what Google's trying to do is to try and get renewable energy in the very same grid, the same location, and the very same time, the same hour. So Google's trying to offset its energy use by buying or arranging for renewable energy every hour in the exact same location. So this is, they call the 24/7 program. So we have now, Google now has gotten up to about, I think, about 70% of all the energy it uses is renewable energy. So renewable energy being, wind or solar or hydroelectric power. But if you look all over the world, it's particularly in East Asia, coal is still a very popular energy source, which is very dirty. So it's there's less renewable energy in some regions of the world than others. So it's got something to do. So how does that affect machine learning? It depends where you build your data centers, or where your computers are located, are affected by what energy you produce. And people are talking about, very almost science fiction. The people at Microsoft signed a contract with a startup company for nuclear fusion, not fission, but fusion, which has been a long desired dream of clean, continuous radiation-free energy. And they signed a contract with this startup company that they'll have a fusion reactor for a data center in 2028. Now, a lot of people are skeptical that that's just a publicity stunt, that they can't possibly do it. But that would be very exciting, right? If fusion energy happens. So that I'd say these hyperscaler companies like Google and Microsoft and Amazon are very interested in finding sources of cleaner energy for their data centers, given we're all worried about global climate change.
I'm sure that Falguni's question is answered from this. Now, moving on towards our next question from Sachi. Sachi is asking, what exciting research frontiers do you see emerging in the field of ML acceleration?
What was the last words? In
acceleration, ML acceleration.
ML acceleration. I tried to put some of those on that slide. Let me go back. For people who do hardware like I do, is we need sparsity is pretty natural in these models. Is how can we build things like with these big systolic arrays? They don't handle sparsity all that well. For large computation, can we figure out a way to take advantage of the sparsity and computation very efficiently? These large language models are very exciting and very expensive, both to train and to serve. So if big ideas there, if you had something that was as effective as Transformer, but much more efficient, that would be a huge, could have huge impact today. I mentioned about, ideas about how can we, maybe it's just behavior to try and get us to create a demand for data centers to be green. As it mentions here in the slide, five of Google data centers are, have 90% of the energy they use is carbon-free energy. If we could try and encourage people to do more of that. There's people talking about ideas like building data centers near big solar farms or big wind farms so that there's no energy loss in the transmission of the energy, and maybe it would do more work when there's more renewable energy and less. So people are all of these areas of innovations either at the data center level, or at the model level, at the hardware level. From a from a hardware perspective, what you want is people who are desperate for faster computers, right? And there's nobody more desperate for faster computers than machine learning. Kind of ironically, Moore's law is running out of steam right when we need it. Because the machine learning, the first word there is machines. We need faster machines to be able to deliver on this exciting things. And so we're going to have to do it without the help of Moore's law, which makes it's more interesting from a research perspective, but more challenging in practice. So this is a very exciting time and lots of opportunities. There's been periods in the past in my career where things aren't so exciting, where you could have what you think is a really great idea, but industry is fat and happy with how things are being done. We're making a lot of money. We can supply the computing needs. This is not one of those times. If you have a great idea, there's plenty of people who want to use your idea.
I'm sure, sir, the question would have been answered. And we will be covering up with our session now. With this, we extend our heartfelt gratitude to Mr. David A. Patterson for sharing his invaluable insights and expertise during this enlightening session. His exploration of machine learning accelerators coupled with the focused sustainability has not only broadened our understanding but also inspired us in envisioning the future. So we express our sincere appreciation for his time, knowledge, and the impactful contribution he continues to make to ever evolving landscape of computing. Thank you, Dr. Patterson, for a truly enriching experience. We thank you from Team Kshitij, and thank you so much, sir.
All right. Thanks for inviting me. I enjoyed the talk and the questions. Have
Thank
a
you
good
so
evening.
much. Thank you.
Bye-bye.